Hello, everyone. All right, just waiting for a few more people to fill in. Did anyone get any happy Prime Day? Did anyone get any good deals on Prime Day?
Not yet.
Not yet. I saw one item that I bought like on Sunday. Actually, I used to have a Fitbit, but it broke. So I got this Mi Band. It's like a Chinese Fitbit, and then I bought it for $50, and then it's on sale today for $35. So I'm gonna have to return and rebuy it.
Yeah, I just bought a Kindle for $140, and now it's on Prime deal for $100.
Right? Yeah. So they're not gonna give you. You have to return it. I asked them. They can't like give you credit back, which is really annoying. Which Kindle did you get?
I bought the Kindle Paperwhite.
Nice.
Yeah.
There's a lot of good stuff. Like I didn't know on the you can even get like comic books and in the Kindle lending library, and it's all free.
Yeah, I just get stuff off the library.
Yeah.
It's easy and it's free, so.
Does the school connect with the Kindle library? Like, can you guys get stuff on your Kindle from your school library or any San Diego libraries?
You could get it off the San Diego County Library for ebooks because the public library doesn't work with Kindle, but it works with like Nooks and stuff. So you have to go off the county only.
Oh, I see. Yeah, I remember a while ago I tried to do that, but I couldn't figure it out. All right. So I don't know if you guys noticed, I posted a practice midterm, and I realized that there's still some topics that we need to cover before you guys are ready for that test. So I'm going to push that test back to Thursday, and I think today and through today and tomorrow, we should be able to cover all of the material, and then you'll have a week to essentially prepare. And half of it is also stuff that you can start, like one good study strategy, especially if you're not very confident with the, like if you're kind of new to the word problems that we did, and you still feel a little bit shaky, a really good approach is like maybe tonight or tomorrow, just do those problems that I mentioned that you have seen already, like I could look it up exactly, but let me just pull it up. So on the practice exam 2, so number 2, 3, 4, 5, and 6, those are all questions that you've seen before. So those are really good ones to practice like tonight and tomorrow. And then, just write them on a separate page. And then next week, just do them, redo them. It's actually really, really good. It's like driving to the same place more than one time. It's okay even if it's the same numbers. It just kind of refreshes you in your mind how to approach the problem. What are the main steps? What's the big idea? So that's a really good approach. And yeah, so let's try today to get through most of, the goal for the next 2 days will be kind of to review or cover the questions 1, 7, 8, and 9, those types of questions. And this is from a previous class, but I think I think this is a good chance to learn those questions as well. Okay, so let me share my screen. Okay. Okay. So this is stuff from, let me see which section this is, because I think we jumped a chapter. Yes. So this is actually something that I think I skipped accidentally. Okay. And I don't think I'll assign too much homework from this chapter, but I do want you guys to be familiar with there's some really important idea. So this is chapter 7. Functions and graphs. And let me just pull up the chat. Okay. All right, so functions and graphs. So does anyone from a previous math class remember what is the definition of a function? How should we think of a function? Anyone want to volunteer? Does anyone remember? And you can also chat me or just say, a function is a mapping that sends elements of one set A into elements of another set of a set B. So this is kind of a really abstract way to think of a function. So a function, we write this way. We say that it goes from the set A and it maps things to the set B. And so one student asks, They didn't remember the exact definition, but they said something like, isn't it like g of f of x? And we're going to talk about things like g of f of x in a little bit. But in general, yeah, a simple example is you can draw it, you can represent it as a pair of two sets. So let's say we're going, we're assigning some quantity to each, or some value to each member of the set A. So let's say we have set A could be the set Alice, Bob, Cindy, Dan. This could be the set A. And the set B could be like their zip codes. So you could have 92109, their current zip code, 92123. Does anyone know another zip code in San Diego that I don't have here?
92117.
Okay. 92117. What area is that one?
Bay Park.
Claremont, I think.
Okay.
Claremont Bay Park area.
Gotcha.
92123.
92123? That's mine.
No, 92113.
Oh, where's that one?
It's like the south area, I think. It's where I am.
Okay.
I forgot what.
Okay, so we got everybody's zip codes here, and what we're gonna do is we can draw an arrow to represent. Okay, Alice lives in 92109. Bob lives in 92117. Cindy maybe also lives in 92109. That's okay to happen. And Dan lives in 92113. So it's okay if two people live in the same zip code, but one thing that's not allowed in this situation is, and maybe zip code is not the best example because people can have multiple like residences. But if there's your primary residence, you'd only have one zip code. One thing that's not allowed is you can't have one person go to many zip codes. So every time you input somebody from set A, you can only get one output from set B. So this is called, so the main thing with a function is a function is a rule that must be a well-defined rule. So a function must be a well-defined rule, which is a fancy way of saying for each input, there is exactly one output. You can't have multiple outputs. It's kind of like it's like a robot that you know exactly what it's going to do. Or it's maybe not like a robot, but maybe like a factory where you put in something and you know exactly based on the process what's going to come out. There's no guessing. Okay, so the set A is called the domain. So the set of allowed inputs the set of allowed inputs is called the domain. And the set of outputs that are actually reached, and there's some kind of, there's some different terminology here, but we're just going to say the set of outputs that are actually reached are called the range. So in this case, the range would be all the zip codes except 92123, because for our function, no input got us to that zip code. Okay, so this is kind of the abstract idea of a function. But I think many of you have seen functions in a slightly different context. Oh, before we move on, you guys can message me in chat, or somebody could raise their hand. Can anyone think of like a similar function? Like, this is a totally open-ended question. I'm curious what you guys come up with, and I'll list some examples that you guys chat me or suggest. What are some other functions that you might encounter or in real life? What can you think of any kind of functions? Not like f of x equals x squared, which we'll do that in a second, but just like functions like this, kind of that you give it an input and you get out some unique output, or you get some well-defined output. Can anyone think of other sort of functions like this? Address, nice. So maybe name the person's name and their address. And instead of just address, maybe we'll do their primary address, because if it's just their address, maybe they have multiple addresses, and that wouldn't be a function. Oh, IP address. Nice. Name to IP. Let's do IP address. Sure, I like that. Your IP address is unique at the moment. Oh yeah, name to phone number is good. Assuming you have only one phone number, so maybe your primary phone number. You don't want to do, some people have multiple phones, so you want to do primary phone. Yeah, I see another one. The name, your name, and the grade in the class. Or maybe you can also, for functions, you don't need to just do one input. Your input could be a pair of things. So name and class, and then you can also have your grade. So you don't just need to input one thing. Address to neighborhood school. Yeah, well, that's good. So name, and then if you, some people mentioned name and your school. Your school address, or the actual school you attend. Very good. Can anyone think of one that doesn't map name to something else? And this is just totally like it can be like, yeah, it could be, something from breed to dog. Let's see. Oh yeah, so let's see. How would I think about that one? Breed to dog. So like you give me a dog, and then I tell you what its breed is, and maybe it's a mixture. That one might be tricky if it's a mixture of breeds, but you could definitely define. Okay, yeah, maybe, yeah, the opposite. Well, you wouldn't want to do the opposite, the inverse function. So once we suggested breed to dog, that would be tricky, because if like you say, oh, Cocker Spaniel is the breed, what's the dog? There's lots of dogs that have that breed. So that would not be well defined, because you wouldn't know which dog to pick. Oh, okay. I see Kanjit suggested check to money. I like that. So maybe like the check number and then the money amount that it's for. So like a check number. Actually, let's see. Check. Yeah, check number. Assuming this is like you have a checkbook, and these are this is the different, and this is the amount. That's a good one. Age to generation name. What does generation name mean? Oh, like Gen Z, millennials. That what you mean? Yes. Oh, that's a great one. Yeah. So There's some ambiguity there though, but like it's like people who are maybe in their early 20s or late teens, I don't know, like maybe there's some boundary, but if you define it very well, Gen Z, millennials, are you guys considered Gen Z or millennials?
Gen Z.
You guys are Gen Z, okay. What does the Z stand for?
I have no idea.
Okay, I see. And then what's the generation before you guys, or after? Like what's the younger
Gen
generation?
X, I think.
That's the younger one.
I think that's the one before us is Gen X. But
Oh, I
I'm not
see.
totally sure.
I think the ones after us are Gen Alpha. I'm not sure.
I see. Yeah, I think I'm in the millennials. Maybe not. I don't even know these days. X is before. I see. All right. Well, we'll leave it to the next generation to figure it out. Okay, Gen Z for short, are the demographic cohort succeeding millennials and preceding generation alpha. Okay, very interesting. Okay, so yeah, so that's a good, if you define that clearly, which sometimes it's not, you can say Gen Z or millennial. You can give the, or baby boomer, right? That's another one. Okay, so very good. So you guys have a feeling that functions are not just like f of x equals something. It's a way to assign a well-defined value to elements of a set. And for example, for the for the function that tells you give them an age, you put in an age into this function and you get out what generation you belong to. It wouldn't make any sense to put in tomato. Like tomato is not an age. So that would be an example of something that's not in the domain of that function. You need to put in a number. You can't even put in a name in, right? Because you just need to put in an age, depending on how you set it up. All right, so now let's go to normal functions in math. So in math, we represent functions, we can write a formula that tells us you put in a number and then you do something to that number. So let's say you do x squared plus 3. So this is an example of a function that we're going to work with. So this is a rule for what to do to the input x. And of course, there's an infinite number of inputs. Like in our examples, you might set it up like, okay, maybe just the people in the class and their zip code. There's maybe like 40 people in the class, and you can create a mapping to each of their zip codes, and you can just create a little chart or something like that. But here, it wouldn't make sense to list out like what happened, like make a table of what happens to every x that you put in. So instead, what we do is we graph it. We draw an x-axis, which represents our different inputs, and we draw our y-axis, which will represent our output. This is the outputs. And we plot our assignments of what happens when you plug in an x and what do you get out. We plot it as x. We collect the points x comma f of x, and we plot it as a graph. So can anyone tell me what the shape of this graph is? What does it look like? Does anyone remember, or has anyone seen this before?
Is it a parabola?
Nice, Hannah. Yeah, it's a parabola. And how is it different than the basic parabola that you might have seen?
It's not at the origin, it's up 3.
Perfect. Yeah, it's just pushed up by 3. Okay, awesome. And we're going to do a whole section on parabolas, but this is just an example of a function. You plug in different values of x, like if you plug in x equals 1, out, when you plug that in, you're going to get out there, you're going to get this point. You're going to get y equals 4. So this is just this is called a graph, and it's a nice visual way to see how the rule, what the rule does to different values of x as you move along the x-axis. Does anyone remember what visual thing do we need to look for in order for a function to be well defined? There's some really important test for a function to make sure that it's a function.
Is it
Isn't
the
it like-
vertical line test?
Yes, perfect. Was that what you were going to say also?
Yeah.
Awesome, nice. You guys remember that, very good. So yeah, it's the vertical line test, because if you think about it, the vertical line test tells us that the graph of y equals f of x should only, and let me cut this, cut over here. Should only intersect a vertical line at most once, since this means f is well defined. So this is called the vertical line test. And if you think about that, that should be pretty clear, right? Because if the graph intersected a vertical line more than once, then that tells you when you plug in that x, which output do you go to? It's not clear. So and a function should never be ambiguous. A function should always be well defined. Does anyone know in this example though, we have if we do a horizontal line test, there's places where it crosses twice. Does anyone know what that's called? So a function can fail the horizontal line test where it crosses more than once if there are inputs that give the same output. In this case, it's going to be in our picture. It's called we call this many to one. So many inputs go to the same output, or sometimes also it can be called 2 to 1 if there's exactly 2 inputs that go to the same output. Otherwise, if it passes the horizontal line test, the function is 1 to 1. That's how we write it, 1 to 1. Okay, so let me kind of go over some of this. And the idea here is just some terminology, but the idea is really simple. What do you guys think? This first function of name to zip code, is this a one-to-one? Like this exact example, is this one-to-one, two-to-one, or many-to-one? What do you guys think?
2-to-1.
Nice. And why is it 2-to-1? And you could also technically say if it's 2-to-1, it's also many-to-one as well. That was kind of not a good question. But yeah, is it 1-to-1 or 2-to-1? Why is it 2-to-1?
Because 2 inputs go to 1 output.
Exactly, nice. And if you were going to do this in real life, like actually let's do our class and get everyone's zip code, it would definitely be many-to-one, because I'm sure many of you have the same zip code, not just 2 people. Okay, good. And then do you guys see that this example here, what's another number that gets us to the output of 4? Can you think of another output that gets us to 4? What else can we plug in for the input for f of x that would get us to y equals 4?
-1.
Perfect, exactly. It's the other place where that, if you were to draw the horizontal line, it would be any place that would intersect this horizontal line y equals 4. And this happens to be also x equals -1. Great. So this is still a perfectly good function, but there's something about being many-to-one that is important, because the idea is that if a function is many-to-one or 2-to-1, it's going to be hard to go backwards. So the inverse function, which goes from the set B back to the set A, is not going to be really a function, because you're not going to know where, like if I tell you, oh, I know a student that lives in zip code 92109, what's their name? You can't go backwards. So that's kind of the important thing about one-to-one versus many-to-one is that you can't invert a many-to-one function. Can anyone think of, like, just going back to these examples, can anyone think of a real life one-to-one function? Or pretty much one-to-one? I like that. Okay, name to phone number. Yeah. So name, like when you see somebody's phone number. Yeah. Yeah, when you well, that's arguable, I guess. Maybe 2 people, if you live in a house with people, like back in the day. Nice. Yeah, back in the day, maybe it would be like a whole family. So that maybe then it's could be arguable if that one is, but that's if it's like your personal cell phone. Okay, good. So Social Security, Aiden suggested Social Security. Gabrielle suggested person to passport number. Name to favorite color, that wouldn't work because a lot of people have the same favorite color. So that wouldn't be one-to-one. So I like a name to Social Security. Even though I think technically, you guys might know more about this, so you can correct me. I believe they sometimes, if someone passes away, they might reuse their Social Security number later. Name to passport number. Nice. So I think these are all good examples. Name to your unique email. That might be good, but again, there's like, if you ever like contacted a company, some emails, actually, yeah, name to, well, what if people share an email account? That's where I would hesitate. Person to their DNA sequence. Okay, Aiden, can you think of a counterexample from person to DNA? Why might that be not one-to-one? Twins or
The 3 of us have the same DNA, so it wouldn't work.
Triplets, yeah, very good. So maybe not. Okay, good. So, so this is kind of the basic things about functions. Now let's talk about the question on the test, which is to define what is the domain of the function. So how do we find the domain? We say domain of f of x. And the rule is these types of problems are pretty simple because usually I'm going to want you to like have an understanding of what a function like looks like, what a formula does. But in this case, you don't really need to worry too much about like what the actual picture of the function is. Just need to think about, okay, in this formula, what are the things that can go wrong? What are the numbers that I'm not allowed to plug in? So let me show you some examples. Let's say f of x, and there's some kind of basic rules that we'll encounter. So let's say f of x equals x minus 7, square root of x minus 7, all over x, let's see here, 7, all over x minus 10. Okay, so this is some function, and you can graph it on Desmos. Maybe we'll take a look later what this looks like. This is maybe a fairly complicated looking graph, but all I'm asking here when I ask for the domain is what are the things that we're allowed to plug in? And you can either, we'll see a way to describe it as using interval notation, or you can just draw it on the number line. But for now, let's just think, what are the numbers that you could plug in? Or in other words, what are some numbers that would give you problems if you plugged in? So can anyone suggest anything that would give you some problems? Nice, Archer. What do you think about the numerator? So you want to share what you wrote there? Oh, okay, no problem. Yeah, so Archer said that x should be less than or equal to 7. And that's a good observation. Oh, sorry, x less than 7 is going to be problematic. Because if you plug in a number less than 7, you're going to get the square root of a negative number, which we'll talk about later. And you might have seen that that's something called a complex number or imaginary number. But anyhow, it's not a good output. It's not going to give us a regular thing that we can just graph on the y-axis. So in order for the numerator to make sense, we want to make sure that whatever is under the square root, anytime you see something under a square root, we got to make sure that it's greater than or equal to 0. Has to be greater than or equal to 0. And then solving this inequality, you get that x has to be greater than or equal to 7. And then, nice. And so Lily also mentioned that 10, you don't want to plug in 10 because that's going to give you a 0 in the denominator. So in the denominator, you don't want 10. So we say we don't want x to be equal to 10. Okay, that's pretty much it. So now the domain is just going to be a description of numbers that are greater than 7 and not equal to 10. And I'm going to graph this. So I'm going to graph it on the number line, which is going to be a nice way to describe sets of points. So this is going to be, here's 0. Here's the number 7. And here's the number 10. And I do a filled in circle at the number 7 and an open circle at the number 10. And I bold, maybe I can do a different color, maybe like purple or something. I can color in the points that are greater than 7 and not including 10. And I demonstrate that by drawing an open circle there. Just give me a yes or raise your hand if you've seen this closed circle, open circle thing on the number line before. and know if you have it. Okay, awesome. And we're going to do a bunch of stuff with the number line. And then does anyone know another way that you can describe this collection of points if you don't want to draw a picture? Nice. Yeah, we can do. There's actually two other ways, and I think we might have talked about them. There's the interval notation, and then there's the set notation with the bar. So you can write it like this. So there's two other ways. We can write it as a set. So the domain is equal to the set of x. This is the condition such that x is greater than or equal to 7 and x is not equal to 10. And I'm not really going to do this notation too much. Instead, I think what we're going to do is something called interval notation. So we're going to go from 7 to 10. I want this, and it looks like coordinates, but it's interval notation, and usually the context makes it clear. So if you write the number on the left first to the number on the right, and what you do is if you want to include the number on the boundary, I always think of putting this bracket. Looks kind of like a door, right? Because it's rectangular, and I think that when I write the door, it's like you close the door shut, and you got like the number like a little finger that just got caught in that door by accident. So that's how I remember it. So that way the 7 got stuck in the door. And the 10, you put in parentheses because the 10 is not inside of the door. So that means that's this interval from 7 to 10, not including 10. And then you draw a U for union, or it also stands for the phrase or. And then you go 10, comma, infinity. And you put, again, a parentheses there. And you can't close the door on infinity, right? It goes on forever, so you have to put a parentheses on that one. Okay? This is called interval notation. And we'll do some more practice with it in a second. But let's do one quick example. You guys try out on your own how to find the domain of f of x. Are there any questions on this example? Because I threw out some new notation here and maybe some new ideas. So any questions before we do an example you guys to try your own? Any questions? Okay, so let me give you guys one to try. So find the domain of f of x equals square root of 3x minus 1 all over x minus 5. Yeah, let me do an interesting one here. Let me do this. Kind of make sure you guys keep you on your toes a little bit. X squared minus 7x plus 12. So this is going to combine some ideas that we saw earlier. So see if you can start this one and find the domain and express it in interval notation. Express in interval notation. Before you jump to interval notation, though, make sure you draw it on the number line. That's always the way I do it. I always like to draw first on the number line, and then I like to do it. So I might also ask for when you finish, if someone can volunteer to annotate the board, that would be really awesome. And if you ever want to annotate or draw something, or you want to show something, show some of your work, I think you can also join the Zoom class from your phone or from an iPad, and it's like a little bit easier to draw, so you're not using a mouse. In addition to the computer, I think you can join from multiple places. Okay, let me know if you need some help where to start. Maybe I'll put kind of put the other steps here so you can take a look at that. And message me, yeah, message me. A few students are messaging me some good questions. And remember, the whole thing with the first question with like square root of x minus 7 is however complicated it looks under the square root, you need a simple inequality to be true. You need that entire thing to be greater than 0. So that's kind of always a good starting point, is whatever's under a square root has to be greater than 0. Whatever is the denominator cannot be 0. Yes, so a good question, square root. The thing that we're not allowed to do for square root is we can't plug in a negative number overall. So if it's some complicated expression in there, you just need to make sure that that expression is going to be positive. Nice. All right, so Lupe is going to annotate for us a little bit.
Well, I'll try.
Yeah, try your best. And if you need me to write any part, just let me know.
Okay.
Nice.
That's what I got for the top, the numerator.
Excellent.
And then for the denominator, I just factored and I got x plus 3 and x plus 4.
Oh,
and,
minus x minus 3, x minus 4.
Oh, right. My bad.
You good?
And I got x cannot. Wait a minute. Hold on. I wrote down my problem incorrect.
Oh, okay. You got
I put plus 7x instead of minus 7x.
Gotcha. Okay.
So
no worries. Good.
Are these supposed to be positive or negative?
So that would be positive for ours, but for your problem, it would be for the one you wrote. You got it right. Good.
Okay.
Nice. Okay. Awesome. A bit. Now from here, did you draw it on the number line?
No.
Were you able to do the interval notation?
I'm about to do that now.
Okay, go for it.
Okay. Can you scroll down? Because I mean, I
Oh,
wrote
okay.
like all over the place.
Yeah. I'm gonna. I can't. The annotation is just kind of like fixed on the board. So I'm gonna.
Oh, okay.
So is everyone okay? Did everyone follow Lupe's work? Is it?
I think I can erase it.
Yeah. You can clear all. Okay, good. All right. So you found the important conditions, and now what would that be in interval form?
Do you want me to write it down? Or
Yeah. Let me draw it first.
Okay,
Just
okay.
kind of because I recommend drawing it, and I know it's hard to draw on the with a mouse, but let me draw it first, and then you can kind of tell us what the. So it would start. Here's the overall x-axis, and then we have 1/3. You found it's got to be greater than 1/3, but it cannot be 3, and it cannot be 4, and it's everything in between. So. How would you write this using the parentheses and brackets and the union symbol? What would you do? Emily, do you want to try? And you can use 1/3 instead of the decimal there. Or anyone want to try to continue to annotate here?
I mean, I could try.
Go for it. Yeah, go ahead, Gabrielle.
So like the annotation with like the domain.
Yeah, exactly. So like
Okay.
just the interval.
So I started a little bit of it. So I got like X and then that line. I don't know what it's called.
Oh, the such that?
Yeah, such that X is greater than or equal to 1/3.
Good.
And X cannot equal 3, and then X cannot equal 4.
Excellent. So that's the set notation. But what about using the parentheses and the brackets and stuff?
Okay, I started that. I think
Yeah.
I did it wrong, but I got the square parenthesis 1/3, comma 3 with the round parenthesis.
Good.
And then I got the union round parenthesis 3 and 4 round parenthesis, and then 4 to positive infinity with the both have round parentheses.
Perfect. You nailed it. Excellent. Not too bad, right?
No.
Yeah, it's just like you got to know that like when there's points missing, you got to use the parentheses. And just goes left to right. You describe an interval left to right. Excellent. Well done. Okay. So that's pretty much it. Now you can also do question number 1. That's how you find the domain, and that's how you would express it in interval notation. And you guys did great. There's other sort of conditions when like a function might give you some trouble, but the only thing that we're going to care about for now is the square root. It's got to be whatever's underneath there has got to be positive, and the denominator cannot be 0. That's pretty simple. That's all we have. Later, when we do logarithms, we'll see some other conditions as well, but this is pretty much it for now. Any questions before we move on? Okay. I do want to show you one other thing about this interval notation, and that's called the and symbol, and you might have seen that before. So this is called, and this is really from Venn diagrams. This is the union. And this is easy to remember because U is like a union. U starts with union. Sorry, union starts with U. And the other symbol is the upside down U. And it kind of looks like an A, but without the bar. So maybe that's one way you can remember it. This means intersection. or this is also means and. So this is, if you're drawing the Venn diagram, if you have a set A and a set B, the union is just combining both of them. So this is A union B. This is like combining the two groups. So if you have like a, are any of you taking any other MESA classes?
Yeah, I'm taking poli-sci.
Oh, nice. Okay, poli-sci, English. So we could do like MESA Math, Union, MESA poli-sci, and some of you are taking both. Some of you are taking only one. But the union would just be like if I say, okay, MESA Math class and MESA poli-sci class, let's all go on a field trip. The union will be everybody who goes on that field trip together. So it's like combining the two sets. And the overlap, which maybe I'll highlight it in green, here is the A intersect B. This is the elements, and this is just the overlap. Let me erase this. This is the overlap or the intersection. So these are the students who both take MESA Math and MESA poli-sci. So that would be an example of the overlap. Okay. So we can apply this kind of notation to any collection of things. Like if you have groups of students, you can do this. But in particular, we did it by, we can also do it with intervals. And there's some interesting things that can happen with intervals when you do this. But let's do a basic question here. So let's simplify this interval. So can you write this as a union of separate intervals? Let me think here. What would be a nice one? Let's say 1, 7 union 10 to 15. I'm going to do it like that. And I'm going to put parentheses overall here. This whole thing intersected with 3, 12, and then put that in parentheses. Okay. So this looks fairly complicated, but you'll see if you draw the picture, it's kind of fun to work out, and it's not that bad. So try to work this out if you feel like you understand what this is asking. Try to work it out. This is an example, and I'm just going to do it by drawing a number on the number line. So I want to find the overlap. This is the overlap, the intersection between a union of two sets, so two separate intervals, and a third interval that I want to see what do they have in common. So let me draw the first pair of intervals that are combined as their own separate thing. So this is the number line. And I have 1, 7, 10, 15, and not drawn to scale. So I have 1 to 7. So I'm highlighting this part, and the 7 is filled in. The 10 is not filled in, but the 15 is filled in. Underneath it, I want to take the overlap. I want to see what does this collection of points have in common with 3 to 12. And this one, the 3 is filled in. And 3, I'm drawing it this way because I know the 3 is somewhere in between 1 and 7. And I know that 12 is over here somewhere between 10 and 15. Okay. So can anyone tell me, in using interval notation, what would be the set of points that that this complicated thing would simplify to? And it might still be a separate set of intervals that are combined. So how can we write this? How can we simplify the result? How can we describe this new set? That's the overlap between, we want to get this overlap. Anyone have any ideas? Message me if you're stuck also. But what are these two number lines? What points do they have in common? And then try to describe that collection using interval notation. So try to figure out basically what, if you try to like overlap them, put them right on top of each other, which parts of the number line would be both covered in bold. That's another way you can think about it. And then try to describe that collection using so I'm hearing some good ideas. Nice. Hannah, do you want to share what you wrote?
So I just started at 3 and then counted all the way to 7.
Mm-hmm.
So then I got the interval bracket 3 comma 7 bracket.
Perfect.
And then I did a union sign,
Mm-hmm.
and I went to 10 because that was the next point, but
Good.
that's not included. So parenthesis and then comma 12 parenthesis because that's also not included.
You got it. Great. So does everyone see kind of what Hannah did there? Let me draw it a little bit. So to think about where they overlap, they definitely overlap here, but they don't quite overlap at 10 because this one doesn't include 10, but they go just over 10 and just below 12. Right, so that's how you can kind of work with these types of problems. So the overlap would be would be just kind of 3 to 7 filled in, and then 10 to 12 is not filled in. And of course, remember that these are real numbers. We're not talking about like integers. If whenever you're doing interval notation, like 1 to 7, you're talking about like the decimals as well. So not just the whole numbers in those intervals. Great. So that's a little bit of introduction into intervals and set notation. So we have about 15 minutes left. I want to introduce one more type of problem, because we already did quite a few different types today. But so far, how do you feel? Just message me really quick. How do you feel about the concepts that we learned today? Was it like a little review? Is it totally new? Is it super confusing? Just kind of so I can gauge where you're at and if we should do more practice. Nice. Okay, some people said review. Some people say totally new. Okay, some people a little bit confused. Okay, cool. Well, so we're about 50-50. Some people, yes, one good comment is I knew most of it until the last example. Yes, I agree. I think the last example is not something that is usually taught too much. Like, but I think it's a nice way to, once you're comfortable with like these open-ended and closed-ended like parentheses and brackets and union and intersection, how you can mess around with them and combine things and get new sets. Okay, how about we do one more practice similar to the example that we just did. I personally find these ones, they look complicated, but they're kind of fun to draw out and solve and set up. So let's try one more. So let's see, this time I'm gonna do, and I probably shouldn't have started with this one because I think this one is fairly complicated. Like it has a union in the parentheses and then you're intersecting it with another thing. Let me see here. I'm going to give you, yeah, I'm going to give you here, this one. Try these two examples. So this is another example. So 3, 8. Intersected with 2, comma. So this is a simpler one. So you can try this example, and then I'll give you one more to try as well. Two, 10. Intersect, and this is in parentheses. -1, 3. Union 5, 11. Maybe I'll, you could maybe do it like this. So I'm just doing the curly braces so it doesn't look like there's too many parentheses floating around. And let me know when you finish the first example, and also if you need any help. And then if you finish the first example, go ahead and do the second example as well. Yeah, Archer, I recommend for both examples, whenever you have an intersection, I like to draw like each thing that is on the left of the, like each thing separate, each separate part of the intersection on its own number line, kind of like this one, and then figure out where do they overlap. You can do these just reading, like visualizing it in your head, but I like to draw it out, and just kind of helps me to see it better. All right, you guys are doing great. I'm seeing a lot of good answers, a lot of answers that are just off by a little bit as well. Let me see here. Any volunteers just to quickly explain 1 and 2? Or just first quickly explain 1? Any volunteers? Okay. Okay, so the first one here, 3 to 8, and then intersected with 2 to 8, but with the appropriate filled in circles. So you can draw the first one is filled in at 3, open circle at 8. So it's like that. And the second set is open circle at 2, and then all the way, oh, sorry, 2 is before 3. What am I doing? 2 is over here. So you do a filled in circle at 8, and then open circle at 2, and you do that. And then you think about, okay, where do they overlap? Well, they're definitely going to both have 3. They got everything in between there, but they don't both have 8. So the answer here, the overlap, would be equal to 3 to 8, but 3 is included and 8 is missing. Because 8 does not belong to the first set, to the first interval. So 8, they don't have 8 in common. Okay, for the second one, hopefully you kind of start to get a feel for them now. You can even sometimes do these without graphing them, but that's a little bit dangerous. You can make a mistake. So here I would draw the one on the left on the top. It just looks a little bit more complicated. So -1 filled in, 3 filled in, 5 not filled in, 11 filled in, and then combining those separate intervals. And then there's going to be somebody like, we'll look at the overlap of some interval that contains parts of both. This will be from 2 filled in all the way to 10 not filled in. And you just kind of think about, okay, what do they have in common? This would be, they get 2 to 3, everything they contain is good. So 2 to 3 is good. But 5 is not in here, and 10 is not in this one. So you get everything except 5 and 10. So the answer would be 2 to 3 in the brackets, union 5 to 10, but both of these are in parentheses. Okay. Yeah, once you get good with the drawings, you could just sort of draw it out in your head, and it's kind of a fun challenge, but it could get pretty confusing. I always recommend to do the drawing. All right, guys. So on Thursday, we will do, I want to do some stuff with inequalities, and also talk about how to use elimination to solve 3 equations, 3 unknowns. If you want to get like a quick jump start on it and practice like that, if you want to try the one on the test, I'll just tell you really simply the idea. So if you have a set of equations, like we saw, like 2x plus 3y, x plus 4y, you can do elimination, get rid of the x. But if you have another unknown, like a z plus 2z, and then 3x plus 5y minus z, and these equal to like different numbers, like let's say 1, 2, 3. So one thing that you can do, is the answer, Lupe asked a good question, is the answer always going to be a union? Yes. So whenever you do these kind of simplification questions, what you're always going to end up with whenever you do unions and intersections any way that you want, the final thing that you get is just going to be a collection of intervals. So you can always represent your final answer as a bunch of unions. That's a very good observation. It might be a single interval that might happen, but it might be, usually it's just going to be multiple unions. We'll do this in more detail. This is just like a quick 2-3 minute explanation. One thing you can do to solve this 3x3 system is we're going to apply elimination, but we're going to apply it in like different levels of the problem. So what we do first is we can eliminate x from, let's say, you pick 2 equations. There's a lot of different ways to do it, like a lot of different paths you can take. But you can eliminate x from any 2 that you want. So you get rid of x. So you eliminate x. Eliminate x. And what that gives you when you do it is that gives you a new equation. And I'm not going to write it out. What would that be? I mean, there'll be something, some equation. In this case, if I do subtract 2, it will be minus 5y z minus 4z is minus 3z equals minus 3. So now you have an equation with just y and z. Similarly, you can eliminate x with another pair of equations, and then you'll get another equation with just y and z. So I don't know the numbers here. You have to do it carefully. Now, once you've gone from a 3x3 system to a 2x2 system, you can do regular elimination where you just eliminate one variable and solve for the other. Then you can work backwards and you find each answer kind of going back up the ladder. So let's say next you'd eliminate y, you'd find z. Then you plug in z, you get y to the equations that one of the equations that you just had. Then once you have y and z, you can plug that into either of the 3 equations that you had before. Yeah, sorry, I made it negative because I multiplied the second row by -2. So let me just kind of show you where that -5. So what I did is I changed this equation to become -2x minus 8y minus 4z equals -4. And then I added it to the first equation. And the x's canceled. The y became -5y, and the z and -4z became -3z. So that's where that equation popped out of. So for example, for this equation that I don't have written down, I would probably multiply the middle equation by -3 and then combine them. So this approach is, solving 3x3 is even more work than solving a 2x2. So you have to be careful with all your steps. And we'll do it in more detail on Thursday. But this is just kind of, you basically just do elimination. You're just kind of doing it, you're turning a big problem into a smaller problem by elimination, but still not solved yet. And then you take that small problem, which will be a 2x2 problem, and then you do elimination, normal elimination on that one. So it's like you're just chipping away at the problem step by step, I guess. All right, guys. I will see you on Thursday. If you have any other questions, I'll hang around here for a little bit, but otherwise, have a good rest of your day. And hope you get lucky with some good deals. This is my watch that I got. See you.